and you guys can give some answers. And we'll probably go for 14 minutes. It'll be a like a speed dating thing as the best analogy I can think of. So let me jump into the first one I'd like to ask. How do you guys, how many tests have you guys had so far? And how do the tests go? And how did you clean your nitrous system for operation? Okay. Who wants to start?
I can talk just like on like the overviewing level.
Okay.
I think I speak for everybody that COVID definitely posed difficulties for coordinating any like in-person kind of testing. And so testing was definitely slow. So we definitely ran different numbers of tests. For example, we were able to have like our test flight to kind of test some first level iterations of designs early in January, February era. And then for example, like our avionics, they had a first iteration of their PCB that we made to run tests and things like that, along with some testing for our hybrid engine, which Savar can talk more about.
Yes, COVID was pretty difficult for the hybrid engine team. We were not able to get around to a hot fire test yet. That's our plan for this summer, but we were able to test some of our smaller components, and we're about to test our pressure test, both of our pressure vessels. So sadly, we're not as far along as we would have liked to been. And what was your second question about the?
How do you guys plan to clean your? If you had a hot fire test, or you plan to, what's the procedure you use to clean your nitrous tanks and your nitrous, wherever nitrous goes to? So
our plan so far was for all the smaller components, was to use a ultrasonic bath with citric acid. I talked to a couple professors who worked with nitrox, the actual material we're using, and they all recommend using this. And I'm not entirely sure what our plan is yet for the oxidizer tank and the combustion chamber, but our designs allow us to remove the end caps, so we're able to get inside. So we will probably use some method of getting inside the tanks and cleaning it that way.
Okay. Okay.
Bob, I've got a question. One aspect of your design that I really liked was some aspects of modularity, where you could exchange your SRAD motor for a COTS motor, and you could take off, remove, and replace an individual fin. Maybe talk a little bit about how you came to those design decisions and some trade-offs, pluses and minuses of those decisions.
Yeah, so I think the biggest like pushing factor for those kind of decisions is just nothing ever goes completely as planned, you know? So especially since our hybrid engine was in development, we wanted to be sure that no matter what, we had a working and launchable rocket. And with that, we've also kind of every year introduced new designs. And so we were hoping to save ourselves money and time, kind of creating more modularized designs could help kind of push our timeline along a lot faster, and then allow for future kind of developments with more groundwork made out. So for example, if Tyler or Myron, you guys could talk more about, I think for payload especially, there's a lot of potential for iterations in the future, things like that. And then the design of the retention system for the hybrid engine also is pretty unique. Tyler, can you explain more? Yeah, or Myron?
Yeah, for the engine, like engine modularity in particular, we kind of foresaw that the hybrid testing phase might be delayed. So we wanted to ensure that we could actually launch the rocket even without the hybrid. That's why we wanted to design it around a commercial off-the-shelf solid motor as well, which did end up letting us test our avionics at least during the January launch. And for the modular fin set, that was mainly due to the hybrid engine. We didn't want to have the conventional epoxy fins that wouldn't allow us to take out the engine. It would have to be like epoxy to the motor or something like that. We just wanted to have like a externally attachable and detachable system. I think the only major drawback to that is that the manufacturing costs were quite high for the custom VinCam pieces. And that's probably the only drawback of that system.
How would it affect the weight and the drag of the rocket?
The FinCam was definitely heavier than the epoxy, and it also did induce a little bit more drag, but because of the hybrid engine, integrating with the hybrid engine, those were necessary compromises, necessary trade-offs.
Yeah, I think that your decision was very wise, but there's always trade-offs.
Okay. Let me jump to back to the fuel. So I got to warn you, I'm a fuels guy. So you talked about you propose using Nitrex for your as your fuel. How do you guys make that stuff, or do you purchase it?
So we actually plan on manufacturing it, and that's something we're working on right now. And the manufacturing process is basically taking commercial nitrous oxide and percolating at a certain rate gaseous oxygen into it, and making sure that's done under like stable configurations. So yeah, that's like a big part of this process for us, is trying to like actually go into instead of just buying fuels for propellants, sort of modifying propellants ourselves and making newer ones.
So you haven't made any nitrox yet then?
No, not yet.
Okay. Do you have any faculty members that have some experience in that sort of chemical processing, or you have chemical engineers that?
We do actually. Our advisor is a chemical engineer who has worked on similar-ish processes, but he's not a specialist in propellants. Our main source of information is Professor Whitmore at Utah State University. He's done a large portion of the research on this propellant, and we've contacted him and gotten actually his procedures that he uses to develop or to manufacture this.
And what percent of oxygen do you propose to put into it? How much extra?
4% extra
4%.
Oxygen into the vapor phase. Yeah.
Oh, okay. Does that change? What's that change the partial? Are you familiar with? My other stint is when I did fuels, I was a physical properties guy. How does that change the density of the since what you're doing, the oxygen is absorbing in the nitrous? How does that change the density? You have any feel for that? You might not have looked at it.
I know. So our team worked on writing a little conference paper about this engine, and I know we've talked about the densities, but I can't remember it off the top of my head.
Okay.
All
right.
I apologize.
Good. That's okay. That's a pretty detailed question. I mean, that's what I did for a living for 15 years, so I wouldn't expect you guys to come off able to answer that off the top of your head. That'd be
I can tell you.
If I can just jump in for a second, I think Dr. Whitmore's paper does mention the densities, and I think it is a slight decrease, but it's pretty small, maybe only.
Yeah, it's a small decrease.
Yeah, it's very small.
But it does help your performance a little bit, doesn't it?
It does.
Yeah.
The main benefit that it adds is it raises the minimum ignition temperature, minimum ignition energy, and that's kind of what we want with it for the added safety benefits.
I have a nitrox related question. So your plan is to have the propellant at 0 degrees centigrade, right, to achieve the right vapor pressure. What was your design for keeping your propellant at 0 degrees centigrade in the northern Sonora Desert at Spaceport America?
So we originally planned to just have our supply of nitrox stored like in like an ice bath somewhere that we could keep and regulate on the ground, and then in the actual tank itself. Myron, actually, you might be able to go over this a little better about how we're cooling the system.
Yeah, so we basically, in order to keep it cool before launch, we store it in an ice bath until filling. And then around our oxidizer tank, we also have aerogel insulation to keep it cool as long as possible.
Nice. Nice.
Very nice. Interesting.
I've got another one, unless you want to go, Rick.
No, go ahead.
All right, so you replaced your long pointy nose cone with a short stubby nose cone. could you discuss how this affected things about your rocket, like aerodynamics and the overall altitude performance and so forth?
Yeah.
Talking a bit about this design beforehand, this was actually something that we were lucky to kind of integrate from previous projects that we have seen, as a sense to save space and weight. It obviously does affect like the stability of our rocket since it does shorten it by quite a bit. But it was definitely an interesting design choice that saved ourselves some time for construction and some resources and materials from having to buy a commercial off-the-shelf nose cone. Myron can actually talk a lot more about the aerodynamics of it and the simulations, things like that we ran.
So essentially, we ditched the larger nose cone because we just didn't need the space anymore. We planned to initially eject our payload, so that space was mainly for additional avionics and recovery hardware for the nose cone. But we didn't plan to eject the payload anymore, so we went with a 0.56 pound lighter nose cone, which allowed us to increase our apogee by 150 feet around.
And what would it do to the aerodynamics?
Um,
I think biggest thing is the stability margin is really throws that off by making it so much smaller. It makes it a bit less stable. We kind of shifted around, especially with our payload design. We had a lot of margin in terms of what material we used, along with a lot of our like technical experiments. Most of the payload is pretty non-functional at the moment. So we had a lot of leeway in the kind of things that we could try and could add to kind of increase the weight up on top to kind of counteract the hybrid engine, especially at the bottom, and increase our stability.
Nice.
And we also modified our fins to account for the difference in aerodynamic performance.
Great.
Let me jump back to the propellant stuff. You guys had a nice picture of your main ball valve assembly. How did you test that thing once you got it? Have you tested it yet with like CO2 or something like that?
Yeah, we actually did that earlier this year. We tested it with nitrogen gas.
Okay.
And so our plan with that was that we just set up a small piping assembly and connect it to a tank of nitrogen gas and slowly increase the pressure and operate the ball valve just to make sure that it would operate below, at, and a bit above our target operating pressure.
Okay.
And we were able to operate it multiple times. So we felt confident that we could comfortably use this ball valve during an engine test, engine flight.
And that controls, as I recall, that controls the main flow from the tank to the engine, right?
Mm-hmm. It does.
Okay. Okay. Did you look at any proportional flows in that, or do you have that capability to control it?
We considered using like more fine control, but we decided that given that our engine burn time is only 4.5 seconds.
Oh, okay, sure. That's pretty short. Sure.
Yeah.
Okay.
We just thought we'd go for full flow.
That's been my choice. Yeah. Yeah. Okay.
But we did actually test in our first design, or when we first designed our assembly, to see if we could do proportional control, and we could. And so we're considering use that for future endeavors because the assembly does allow for it.
Sure. Very nice. Okay. Bob, we got 3 minutes. What do you want to
Yeah. I got that was all the question I had written down. Do you guys have any future plans for things you want to add to the rocket, even if they're not within your current time frame?
I think biggest thing is like each one of these areas kind of for our propulsion, our avionics, our payload, the structures, they all kind of have, of course, future stuff down the line. I think that have been kept in the back of our heads this year. A really interesting one, I think, if Anshuk wants to talk more about like avionics and some of the concepts that they've been incorporating and kind of long-term goals that going forward, that I know they have a lot of plans.
Yeah, I know you mentioned modularity before. Our avionics system also, we try to keep as modular as possible. And so with our avionics system that we call TARS, we have 4 boards on 4 sides of the cube. And we built the first 3. So we have our own custom flight computer board, our independent COTS board, and the power board. We also have a 4th board that's currently empty, but we kept there for expandability. So in the future, whenever we want to add more computing power or more sensors or additional sensors for the hybrid engine, or if you want to do a lot more advanced control simulations, then we can do that on board as we add more computing power. And a lot of the avionics system also is still under development. That we have the PCBs for our final design, but there's still a lot more testing to be done in terms of flight testing with the hybrid engine, and so we plan to do that in future flight tests as well.
Great.
I think the same thing could, sorry, so I think the same thing could be said for payload. I mean, I think those two especially have like the biggest development to go.
Everything in payload is made out of steel, aluminum, or carbon fiber, and it's all can be taken apart because it's all held together by screws, except for some custom-made parts that were welded to the rails. But if we wanted to, say, add a heavier payload with more avionics systems, then what we could do is reduce some of the metal components that we have that are only in there currently because of the acrylic section of the rocket.
Yeah, modularity is.
I think that's it now. We just used 15 minutes. You guys look real good. How many people expect back next year? Team number?
Oh, yeah. Well, it's 113. So we definitely signed up to follow through for next year.
Right.
Okay.
How many of your people are seniors and how many are coming back?
We've got a couple graduating this year. I know Jake, for example, he's a senior. But for a majority, I think, out of the, at least, the juniors this year can plan on it reiterating. I can't tell you off the top of my head how many seniors we have, but we'll definitely have a good amount.
A majority of our team will be back. Yeah.
Well, I'd love to see
All
a
right,
rocket fly.
We're out of time, so we'll see you guys later. Hopefully we'll see you next year, okay?
Thank you.
Thank you.
Thank you. Bye, guys.
Thank you.
Thank you.